So for factoring our quadratic here, notice there's nothing I can divide out of every single term. So that tells me that since it is a quadratic, remember that means it's to the second power, that I'm just going to see what two numbers add to the middle number. In this case, that's the negative 12, and multiply to the last number. In this case, that's a 27. And then when I format my answer, I'm going to end up with the two sets of parentheses since I am factoring a quadratic. And each of those parentheses starts with the x. Now notice I'm multiplying to a positive, but I'm adding to a negative. Does that mean that my two signs are both positive, both negative, or one of each? Yes, they are both negative because a negative times a negative is positive, but if you add two negatives, you get a negative. And then it's just a matter of how do we get the 12 and the 27, and it should be coming up with 9 and 3. And so there's our final factored form. This is what we're going for. Continuing with that practice, please factor these two. So let's go ahead and factor each of these. For that first one, I can see that I'm going to be multiplying to the negative 110. Now, first of all, before I worry about anything else then, since I am factoring a quadratic that's multiplying to a negative, I already know that I'm going to have 1 plus and 1 minus, just based on that information. I haven't even looked at the middle yet. And I'm going to be adding to 1. Because remember when we say plus x, that's plus 1x, and I'm only interested in the number that's in front of it. So I'm adding to 1, multiplying to a negative 110, so two numbers that are only 1 apart, then multiply to 110, that sounds like 11 and 10 to me. Now between 10 and 11, notice that I am adding to a positive. So then which one should be the positive number, the 10 or the 11? Yep, the 11, because I need to have more positives than negatives. And that's how you can quickly get there, kind of what's going on in your head. All right, and then for the second one over there, again, it's a quadratic. And so I'm going to go ahead and set it up as the two sets of parentheses, each one starting with an x. In this case, I'm multiplying to a positive, so I know both signs are the same. And I'm adding to a positive, therefore they both must be positive. And then I need two numbers that add to 13 and multiply to 12. And at this point, I know some of you are staring at it saying that's impossible. But it is possible. Throughout our various algebra, we've almost been trained to ignore the 1 factor. No, literally, the factor of 1. Because 1 times 12 would give us the 12. So if you're missing it, it's understandable because so often we say, well, what can we divide it by? Well, except 1, obviously. You know, we do a lot of that kind of stuff. But in this kind of a case, we do need to consider the 1 as an option. So it's going to be 1 and 12. And so there's our factored form for that one as well. Now today we are continuing with our concept of solving systems of equations. So to start off today, I'd like you please to go ahead and solve this particular system of equations. Now if there's any single mistake that I'm tending to see on these, it's just remembering which way we're moving. Notice in both these equations there's no parentheses. You notice there's no parentheses around the x minus 2 there. That's how we know it's not going in the x direction, but rather why that minus 2 is moving it in the y direction. It's moving it specifically down. So I'm going to start by going down 2 there, and then use my slope of 2, so up 2 over 1, up 2 over 1, etc. from there. And then for the other one, we start up 7. And so we start up 7, and then a slope of negative 1/4. That's going to be like going down 1 and right 4. Or if you prefer, you could go left 4 and up 1. It's going to get you the same place. And then you draw in your lines. And of course, we look to see where they intersect, right, to find our solution. And so our solution in this case looks like it's going to be up at 4, 6. And so that would be our answer. But I actually kind of fed you something here, and you know, I put up the problem and I put up a graphing grid right away because that's what we were doing last week. But you know you don't actually have to graph this to solve it. There are ways that we can do that, and that's what we're going to be looking at this week actually, is looking at how could we take something like this same system and solve it without having to graph it. I imagine you'll probably be feeling thankful for that because you're probably tired of graphing these, right? And so we're going to be taking a look at how do we first solve linear equations without having to graph them. This should again seem somewhat familiar. We're touching on old ideas, but we're really making sure they get nailed down. We're going to get better at them this time as well. And throughout the year, we'll also be extending it into solving other types of systems as well. But for now, we're going to focus on linear. So we're going to be taking a look at how we could solve this particular system just algebraically. So rewrite the system so that we're not having to try to show our algebra on your graph there, and then we'll work it out together. All right, and today the method that we're going to be working with is the old substitution method. And then we'll be working on the other method tomorrow. And so today is substitution. It's called the substitution method because if you know what a particular variable equals, you can actually substitute that value in for the variable, right? Like if I told you here that y equaled 7, I'm just making that up, you know you could substitute that in for y. Well, we're going to do the same thing here. It's just that you can do that with something more than just a number as well. I can actually say, for instance, y equals this whole expression, and I can substitute that in for y. And so there's nothing magical about plugging the second one into the first one in this case. I could just as easily have chosen to take this and plug it in down here. You'll actually end up with the same equation. It'll just be a matter of which one's on which side in this particular case. But let's go ahead and do that then. So that's going to give me a new equation which says negative 1/4 x plus 7 equals 2x minus 2. Notice what we just did is we changed two equations with two variables into one equation with just one variable. And if you have one equation that just has one unknown in it, you can solve that. Now, what's going to make this one hard to solve?
Fraction.
Yeah, that fraction there, right? That 1/4. Now, there's a number of ways you can go about dealing with it. But the method that I find generally helps people the most is to start by getting rid of that fraction, to start by multiplying through by its denominator. Notice that this fraction is 1/4. If I multiply 1/4 by 4, it's no longer going to be a fraction, right? So what I'm going to do is I'm going to multiply everything on both sides of this same equation by 4. And yes, it has to be multiplied by everything on both sides. And so if I do that, that negative 1/4 x, negative 1/4 times 4 is negative 1. So that just becomes negative x. Then plus 28 equals 8x minus 8. Now it doesn't look quite as intimidating because we got rid of that fraction. Having done that, now it's hopefully easy. Let's check and find out. Go ahead and finish solving this out for x. Now for me, I always like to move my x's first. That's just kind of a habit I've gotten into. And I like to keep my x terms positive, so I chose to add the x to both sides first. You don't have to do that first. There's other orders you can do that in. But it's what I chose to do. And then once I did that, then I had to add the 8 to both sides. And we end up finding that x equals 4. Which is good, because in this particular example, we kind of knew that already, didn't we? Because remember, we just solved it by graphing, and here we're just saying how I also could have done it algebraically, how I could have done it without having to make the graph. And when I did that, I found that x was 4. But I didn't just find that x was 4, right? I also found a y value. And such is the case in this one as well. I also have to find the y value. So what do I do to find the y? Yeah, we're just going to plug in that x value that we just found. Again, we're substituting it back in. Now, we can substitute back into either one of the equations. I could plug it into the first equation, or I could plug it into the second equation. It does not matter. But I'm guessing most of you will see that fraction in the second one and decide, I'd rather put it into the first one. And that's fine, because if we did everything right, you will end up with the exact same solution, either way. And so we end up with y equals 8 minus 2, therefore y equals 6, hence a final solution of 4, 6. And yes, of course, that is what we were going for, was that solution. Now, just as a side note, I feel like proving it today. If I did plug it into the second equation, no, you do not have to do it because we already plugged it in and got our answer. But just in case you wanted to plug it in to see, this is a great way to check yourself if you ever are feeling insecure about your answer. If you plug it into both equations, you really should get the exact same answer. After all, the whole point of solving this is figuring out when they are the same. And so, notice, whichever way I did it, I get a y value of 6. So we're still going to end up with the same solution either way, but by doing it a second time, I also just made myself feel a little bit better because I now know that it must be correct, because I would have to have made a couple different mistakes and have them work out just right in order for it to look like it worked both times if it didn't really work out. So this is a really good way to tell yourself that yes, you got it right. Because this, of course, is the point of a solution, right? It's where they're the same. It's the xy coordinate pair that they share. Now in this case, you don't have the same options you had last time. In the last one, you could have plugged in either way. In this case, it's actually really prescriptive about what you're going to plug into what, because we only know what y equals. And so I'm going to take this x plus 5, and I'm going to plug it in for y in the other equation, because that's the only one that I know what it equals. And so it's the only one that I can substitute in. So when you do that and plug it in, this is what your first line of your work should be looking at. And then from here, it's just a matter of doing the solving. It's just a matter of how do we then solve this equation for x. Of course, the first thing you want to do, distribute. Get rid of those parentheses. Which actually brings us back to one of those things that we did back in our first unit, where we were just practicing some stuff. In fact, remember that little squares activity where you cut out the squares and arrange them into the big square? A lot of the problems there had you distributing a negative into the parentheses, because it comes up a lot, especially with problems like this. And we have to remember that when I'm distributing here, I'm actually distributing a negative 3, so it's going to make it a minus 15. If you had written plus 15 there, life would get a lot harder for you, and it wouldn't work out. So make sure you distributed that correctly, then finish solving it out for x. And when you work it down, you end up with a negative x equals 2. Well, logically then, we could just kind of say, well then, it must be that x would be negative 2. Because that's the only way a negative x could then equal a positive 2. But what are we technically doing to both sides in order to get there? Well, generally speaking, what we'll say is we are dividing by negative 1. Although since it's negative 1, technically you could also say multiply by negative 1. It'd still give you the same thing. But then that gives us our x equals negative 2. Now remember, of course, we're not done with this problem, though. We're only halfway done. I still need to figure out what y is. All right, so to find that y value, can we plug it into either equation? Technically, yes. Is one going to be easier than the other one? Yes. I definitely would recommend plugging it into the first equation. You can plug it into the second. You're just going to have to go through some more algebra to solve it if you do that. So then, I plug it into the first. So that's going to be a negative 2 plus 5 equals y. And of course, I'm trying to figure out what y equals. So negative 2 plus 5 is 3, so we end up with 3 equals y. Now, when I get my answer, as I was looking at some people's papers, I was seeing something written like this, which is pretty good, but it's not quite right. I still want to say that this is an ordered pair, that the order matters. Because right now that, as I wrote it, is a list of numbers. This actually makes it an ordered pair where the first one is x and the second one is y. So you do need the parentheses around it in order for it to actually represent x and y separately instead of just two numbers. Having done those, we're doing just two more. Go ahead and now solve this equation, or rather the system of equations. Now after having done the first few, it's very easy to think that I'm always substituting what y equals. But notice I don't know what y equals in this case. So use what x equals. Take what x equals and plug it in for x in the other equation. All right, then as you finish, you can check your answers up here, make sure that you're looking good. Should have gotten negative 2, 4, and we didn't even have to make a graph, did we? Yeah. Now, as you take a look at that, you'll notice the work that I'm showing. You know, when I'm combining terms, I'm just showing from one line to the next. I'm not having to show like what I'm doing on both sides, right? Because I'm not actually doing something to both sides, I'm just combining like terms. But when I am doing something to both sides, I'm showing that. I'm writing out what it is that I did to both sides of the equation. This is the kind of algebraic work that I expect to see on your paper as well. So as we do written assignments and stuff like that, this is what I'm looking for as part of the assignment, is I'm looking to see that you're showing all the work all the way down through. This will be the last one we do together today. Go ahead and solve it on your own first. And in this problem, you'll notice that you're immediately faced with a decision. What are you going to plug into what? Because you could take what y equals from that first equation, you could plug that in for y in the second equation. Or you could take what x equals here in the second equation, you could plug it in for x in the first equation. So which one should we do? I don't care. Either one's going to work. It's up to you. Whichever one you feel like substituting in which, go ahead and go with that. It will work either way. And then just to prove that you could have done it either way, I did it both ways. I showed what it would look like if you substituted the x in for y, and I showed what you would get if you substituted the y in for x. But whichever order you did it in, you should still end up with an answer of 7, negative 5. Now, did you have to do it this way for both of them? No. If you did it this way, you got that x was 7, and then you plug 7 in for x up here. You didn't have to do the other one. But I wanted to show you that if you did it this way first, you could get that y was negative 5. You would then take that negative 5, and you'd plug it in for y in the second equation. And you get your answer that way. But just also showing it works either way. You end up with the same answer either way you do it. It really is choice.